we're going to focus primarily upon two aspects that are a little different than last week. So last week, those are some of my favorite kinds of problems in Trig because you can't cheat on them. You really can't. You can't grab a calculator and plug them in. You can't grab a computer and graph them. It just can't be done. You have to understand how they fit together to do it. Which to some people, it sucks. I'll be honest. I think it's not fun for everybody, but I love them. I think it's some of the best problems that we have in this class, period. Because you actually have to know what you're doing. And that matters a lot. Now, we're going to be looking at similar problems this week, but with a slight twist. So last week, I gave you the beginning, I gave you the end, and told you to find a pathway to get there. Today, we're looking at the more general rules about two categories. How to rewrite, and how to solve a trig identity. The rewriting portion is basically taking a trig function and rewriting it as a specific trig function. So being given one trig function, writing it in terms of only sine, writing it in terms of only cosine, writing it in terms of only tangent. This gives us an advantage if you're using a computer program to solve a math problem. So it's primarily used for things like computer science majors. It's used a lot in web design and game design because it makes the process go by faster if you're only using one function. The second thing we're going to talk about is how to actually just straight up solve a trig identity, where you're told, hey, you don't know what the solution looks like, just simplify it as far as you can. Those tend to be the most frustrating because you don't know what the end looks like. And you're trying to define what the end looks like. So for a lot today, we work through a bunch of examples, discuss why we stop at certain spots, how we get those places. And most of the problems we're going to talk about, most of them come from your homework. So I strongly encourage you to write them down and try them out. Here we go. Our first example. So these problems, we're going to be focusing primarily upon just simplify. So let's look at the first example. We have a trig function listed as sine of theta times cosine of theta times secant of theta. And we're told to simplify. Now, I'd like to remind you guys about something from algebra. The definition of simplify. Simplify means to reduce in complexity. This means to reduce the number of things being added, subtracted, multiplied, or divided, or to reduce the different kinds of things. So in this case, I had three different trig functions. If I could condense it down to two trig functions, that's better. Down to one trig function, that's better. Down to no trig functions, that's better. In general, simplifying is very similar to a trig proof, but you are just not given the end. In fact, the way to do a trig proof is you start by simplifying, and once you have the answer, you ask somebody else to find the path. Let's look at this problem. We're tasked with simplifying. We have sine times cosine times secant. I'm not going to tell you what the end looks like. You got to figure out when to stop. The best way to tell is if I do another change, does it get worse? Do I add more things being added, subtracted, multiplied, divided? Do I increase the complexity? Meaning instead of having one operation, like multiplication, do I suddenly have multiplication and division? Okay? I want to reduce the complexity as much as possible. So take a look at this problem. Sine times cosine times secant. That's simplified. So take that cheat sheet out. We need to find a way to take these three functions, sine, cosine, and secant. Maybe there's a way to rewrite them. Maybe there's a way to combine them somehow using a property or one of the identities. There must be some way to reduce the complexity of this statement. Because right now I have three things, all being multiplied. Is there a way to make this simpler?
Yeah.
How are we doing?
Secant is 1 over cosine.
Secant is 1 over cosine. So we're going to take my first step. I change this from sine times cosine times secant to sine times cosine, and then using a reciprocal identity. How do I write secant?
1 over cosine.
1 over cosine. Why does that make this simpler?
Because cosine times 1 over cosine cancels out.
Correct. The cosine and the cosine, one of which is on top and the other of which is on bottom, will end up canceling, leaving us with just a single trig function. This has clearly been simplified because I went from having three things all being multiplied down to one thing. So this is my solution.
I like these ones better.
Is that pretty much the most basic?
This is a basic example. They get a little tougher, but not much, to be honest. They could use like a different trig identity or force you to use other properties. Like you saw last week, how we had problems that use things like distributing, problems that use things like factoring, things like the square, or combining fractions. Those can all happen in this section too without the advantage of knowing what the end looks like. That can make them kind of interesting. So another one. So, first example.
Pardon the interruption, but you received a list of students who were to attend the Crowder enrollment today. If those students could be released at this time,
Next example. We have, this is one we've seen last week. So sine of negative x times cosine of negative x times cosecant of negative x. Again, my goal, reduce complexity. So, even odds, first place I look to. Why is that the first place I look to in this case, Violet? Because I want to give it those negatives first. The other trig identities apply if there's not a negative on the inside. So if I get rid of those negatives first, I'm in a good spot. Let's talk about each piece then. Go to the even odd portion of the page. Should be on like the top of the last page, if you believe. I did it pulled it up like I showed you in class. Okay, even odd portion. Let's talk about the first piece. Sine of negative x. What happens to sine of negative x?
It all comes negative.
And the negative moves to the outside. The inside drops to just sine. What happens to cosine of negative x? It disappears. It is an even function, so it disappears. Sine is odd, so the negative moves out. Cosine is even, so the negative goes away. What about cosecant?
Goes the outside.
Goes to the outside. This piece becomes negative cosecant of x. Now, these are not subtraction signs. These are negative signs. Remember, all three of these are still being multiplied. So it's times, but it's a negative cosecant and a negative sign. Let's go back to number theory. Way back in September. What happens to those negatives? Yep, double negative. This becomes sine times cosine times cosecant. Now I can start applying some of the other trig identities, the reciprocal identities, the Pythagorean identities. In general, my go-to move is if I can use even odd, I do it first. So I did. Thank you, Madeline. Good suggestion. And good simplification. Now what do we do? This done?
No.
I don't know.
Let's see here. Cosecant is 1/sine.
So, I temporarily increase the difficulty of this problem. Because I have three things being multiplied, now I have two things being multiplied and a division problem. But I do so strategically because of that sign. What happens now? Yeah, the signs cancel. And what's left behind? Just cosine. And this is significantly simpler. That is why it is a solution.
Cosine of x.
And I can easily show this is correct. For those that are wondering how to check your work, type them both into a graphing calculator or into Desmos. Do they generate the same graph? If so, they have to be the same function. So if I graph this function and I graph this function, do they look the same? And this is kind of neat because one of these is easier to graph by hand. Like I can't graph this by hand, not easily. But this, we graph this many times. So this becomes a problem where I can't graph by hand. Suddenly, yes, I can. That is the point of taking these functions and simplifying them down to be less and less complex. But again, we don't know what it's supposed to look like. So we could have just simplified the x's, put the negative outside and simplified that. Like, I think it's done. But again, the goal is to reduce it as far as you think you can. Let's look at one that's a little bit tougher. Example number 3. See what you think of it. Ooh. Ooh. Let's see what could happen here. 3. Sine cubed. T. Times cosecant of t. Plus cosine squared of t. Plus 2 cosine of negative t. Times, last thing, secant of t. Alright. Wait. Sorry.
Is there more?
Not secant. It's cosine. Alright. let's simplify this thing.
I think this.
Don't do that. 'Cause when you're done, you'll be like, oh, when's the bed? I like problems like these because these can look like the devil. But once you take your time, just do one little step at a time, you start to simplify very, very quickly. In fact, the answer. Alright. Try this out. I look at a problem like this. What draws my eyes first? I'm told to simplify it. What do I do?
Yeah.
Let's get rid of that negative. What happens that's negative on the inside here?
It goes away.
Why does it go away?
It's even.
It's an even function. And even functions, value goes away. So 3 sine cubed of t times cosecant of t plus cosine squared of t plus 2. The negative goes away because it is an even function. I'm left with that. All right. So far, I've reduced the complexity. What next? Darton? Just dying back there.
Do we combine the cosecants to make it squared?
I don't have multiple cosecants. Oh, you mean right here?
Wait, what? I have multiple cosecants.
I don't see multiple
You
cosecants.
told me the last one was a cosecant.
Nope.
You definitely said that.
No,
I did
he
not.
said change. Yeah, he said.
He said no, it's cosecant.
I said, oh, sorry.
Oh my god, I hate you.
You have to check the video afterwards and show you. All right. What can I simplify here?
Damn. Alright.
So
It is.
2 cosines can multiply.
Okay.
To make cosine squared.
All right. So he's going to take this cosine times that cosine and get cosine squared. That's good. I like it. 3 sine cubed of t times cosecant of t plus cosine squared of t plus 2 cosine times cosine you said was cosine squared of t. That's less complex. I went from having 1,
Yeah, I got
2,
a
3,
question.
4, 5 different things down to 4.
I got a question.
Go ahead, Sui. I'll get you first.
That was also cosine of squares, so wouldn't you add that to the other cosine?
Yes, we should. Algebraically. As a reminder, algebraically, if I have something squared and something squared with 2 of them, I can combine them together as if they were x's. So if I have an x squared plus 2x squared, I would get 3x squareds. But if they're cosines, I'd have 3 cosine squareds of t. Very nice of me. So I have 3 sine cubed of t times cosecant of t. And if you're seeing a different step, you may do more than one step at a time for these problems. Just make sure when you simplify them, you simplify them correctly. You should always know what's at the end, if you did it correctly, that they should look the same if you were to graph these functions. Got some suggestions? Hold on. Cole, did you have a different suggestion?
No, I just have a question.
Sure, go ahead.
What happened to the negative t?
So, as a reminder, up here,
Yeah.
this is an even odd rule. Madeline? So she says, let's rewrite this cosecant as 1 over sine. So we get 3 sine cubed of t times 1 over sine of t plus 3 cosine of t.
Cosine squared.
Cosine squared, thank you. And what happens next, Madeline? 1 of the cosines cancel, leave me with what? 3 sine squared of t plus 3 cosine squared of t. The most common mistakes in these kinds of problems are the algebra. You cancel a sign, you drop the power, not the coefficients. So the sine cubed cancels with one of the signs and becomes sine squared. Say what? No? This looks pretty dang good.
Are we done?
There's one more thing that can happen.
Oh, the.
I know for a fact there's one more thing.
Squared, yeah. So it equals 1.
Would it be 3?
So, I have to do some changes here. So if you look on your Pythagorean identities, you might notice that there's something similar here.
So do you factor out
So I'll factor out a 3. And what's left behind? Sine squared of t plus cosine squared of t. And according to Pythagorean identities, sine squared plus cosine squared is always 1. So I get 3 times 1, which is 3. Oh, look at that. It's right there the whole time.
Why did you? What?
He said he had it on his name.
Why did you write it there? Wait, did you do that in your head or did you just know the answer? Did it in your head?
No, he knew the answer.
He did the answer.
He definitely.
He looked in the book and wrote it. If you say so.
All right, now, if I'm telling you the truth here, we showed a lot of steps in here. We could have shortened some of these steps down, done more than one thing at once if we wanted to. I'll leave that much up to you. You should have some steps shown, though. And if you can do these in your head, then you should get your teaching. Okay?
Go ahead.
So, notice how we started this problem? We started this problem with this big, nasty equation, right? Like it took up the entire board. And it reduced down to 3. And here's the thing, if you graph both these, they're the same. It is a constant graph going across the 3. Because that's how the functions work. That's why it's so important to simplify, because if you're doing these with the computer has to take time to simplify all those little pieces. And if you're running things like a graphics engine for your phone, for a website, for a game, that time spent doing those calculations is time that is causing you to have latency. If you like the game, it's something you don't want. Questions? Notice each time our goal becomes to simplify, to reduce in complexity, to get down to something smaller, using trig identities, using algebraic identities, using magic. Okay. Next example. All right. Here we go. Negative sine of negative x, cosine of x, secant of x, cosecant of x, tangent of x, all over cotangent. Next problem. Okay, we saw the last one simplified really far. Let's see what happens to this one.
Wait, why'd you turn off?
I didn't. Or turned off on its own. There's a ghost. There. That's the next problem. Negative sine of negative x times cosine of x times secant of x times cosecant of x times tangent of x all over cotangent. Alright, we saw the last one simplified really far down all the way to 3. It's not common to simplify that far down, but usually pretty close. These should reduce in complexity by a significant amount. So, let's talk about this problem. Now, if I'm doing this problem, I'm probably going to take care of this negative first. That does not have to be the only first step. There could be other things we do. So I look to your suggestions. What do you want to do first?
Whatever I done for free, come on.
So sine. So the negative would go away, right?
Yes. Why does the negative go away?
Because you're arguing on the outside, and then you're moving the inside to the outside.
So we move the negative from the inside to the outside. That's an even odd rule. But there's already a negative. That's going to make it positive. So it's going to give us the following function instead. We'd have sine. And now it's frozen. All right, fine. I'm going to do it over here. We'd have sine of x times cosine of x times secant of x times cosecant of x times tangent of x all over cotangent. Okay, I'll need you one for today. All right.
Then you can just take the tangent away pretty much, can't you?
Actually, no.
Well, it'd be 1 over cotangent, 1 over cotangent, right?
So then I'd have 2 cotangents. Because I already have one on the bottom. Let's simplify some other stuff first. Actually, that's the hardest part about this problem is the tangent and the cotangent. Let's take care of some of the obvious ones. What else can I simplify?
Secant's 1 over cosine.
So secant becomes 1 over cosine. And why is that helpful?
You just cancel out the other cosine.
Okay, and what about cosecant?
Cosecant turns into 1 over sine, right?
And why is that helpful?
Cancel out the sine.
So the secant cancels out the cosine.
It'd just be tangent over cotangent.
Yep. The cosecant cancels out the sine. And what's left behind is tangent over cotangent. Now, at this point, I want to raise the next piece you need to know about simplifying. So I said to you before, simplifying is about reducing complexity. In Trig, the 3 basic trig functions are considered less complex than the 3 advanced trig functions. So if you have a choice between sine, cosine, and tangent, or secant, cosecant, and cotangent, if those are your 2 choices, always put it in the first 3, sine, cosine, and tangent. It is considered to be the better way. So at this point, I could write this in terms of cotangent. If I wanted to. I convert tangent into cotangent and start solving. Or I can convert the cotangent into tangent, also using the reciprocal rule. Both are accurate, both are true. One is considered to be more simplified than the other because it's basic. Alright, good people, you want to stick with basics. Alright, so what should I do next? Keep that in mind.
Turn the bottom to 1 over tangent, right?
Okay. Turn the bottom. And 1 over tangent.
Then this is just tangent squared of x.
Now, at this point, we had a rule last week about dividing fractions. It was an algebra rule from Algebra 1. I hate you so much right now. There you go. So what you do is we put the top over 1. You want both pieces to be fractions, and then you multiply by the reciprocal of the bottom. So the first piece, tangent over 1, stays tangent over 1. The second piece becomes multiplication instead of division, and we flip it over, the reciprocal. So instead of 1 over tangent, we'd have tangent over 1. We then multiply top to top and bottom to bottom. Tangent times tangent is tangent squared. 1 times 1 is 1, and dividing by 1 doesn't really do anything. So this is the correct solution. Now, if you look on your Pythagorean identities, there's a way to rewrite tangent squared, but it doesn't make it any simpler. It turns into 1 minus cosecant squared, I do believe. Or sorry, it's 1 minus secant squared. So there is a way to keep going with this, but your goal is to get it as simple as possible. I have one term, it is squared. That is simpler than 2 things being subtracted, as weird as that sounds. This is considered to be the most simplified version. It is what your book would show in the answer page. It is considered to be the most simplified. One more time. Our goal is to reduce complexity. To take the number of terms and lower it, to cancel what we can using either reciprocal rules or algebraic rules. And then with those rules, get them as few terms as possible. Notice we had to apply some algebra to get this fixed, as was common last week. But unlike last week where I gave you the solution, these ones are trying to find it. Now, one last thing to talk about. So this is solving a trig identity. Let's talk about rewriting. Rewriting is a slightly different concept, and in my opinion, is the easiest of the 3. Mainly because it tells you how to do it. It tells you where to go. So we put a problem on the board. Let's talk about it. And the following problem. Let's see. we have tangent of x plus cotangent of x all over cosecant of x. And I am told I need to rewrite this trig function, not simplify. Notice in these problems you're going to have in your homework, they will not say to simplify. They say simply to rewrite. However, I want to write it so that everything is in terms of cosine. That means that tangent is wrong. That cotangent, wrong. That cosecant, wrong. Everything must be a cosine. I have to find a way to rewrite every single part of this problem so that only cosine appears in my answer. Now, it's going to have multiple cosines. Some being added, maybe some subtracted, some being multiplied, some being divided, maybe. I have to find some way to rewrite this function so it has just a single trig function in it. Now, let's talk about some things that are helpful for these problems. One, the reciprocal rules. Reciprocal rules allow you to take most of the trig functions and convert them into sines and cosines. The quotient identities. They allow you to take things like tangent and cotangent and reduce them to sines and cosines. That's a good starting place. Otherwise, my goal is to only have cosine in this problem. Let's talk about some steps. Here's our problem. Tangent of x plus cotangent of x all over cosecant of x. My main first goal, again, follow similar steps to over there. Where I look at it and say, okay, I want to make sure I look at my solution, make sure I'm guiding myself to it. I want to have only cosines in it. And especially rule number 4. If all else fails, convert into sines and cosines. I need to rewrite this function with just sines and just cosines. So, let's talk about some good first steps. One good first step, convert everything into a sine and a cosine.
Can't do that with tangent.
Hey, again,
Wait.
it's a quotient rule.
And
Also do with cotangent.
then turning that into cosine over sine.
Cotangent
Bottom
over
of
cosine.
1 over sine.
That is one good first step in this problem. I could convert everything into sines and cosines. Option number 2.
The top would cancel.
Some of it would, yes. Option number 2. To somehow take this problem and just fix the fraction. That is actually totally reasonable. I could rewrite this fraction in multiple pieces like we talked about on Friday and Thursday as an algebraic rule. But again, it's a little bit different. Alright. I'm going to follow Garrett's advice. I'm going to use the quotient rules to fix the tangent and cotangent. I'm going to use the reciprocal rule to fix the cosecant so that everything becomes sines and cosines, which means for a while, this is going to look a lot worse. Accept that. Move past it. Let's take this step. Here we go. We get tangent. Garrett, what does tangent become?
Sine over cosine.
Thank you, Cole.
And then cosine
Over 1 over sine.
over 1. Yeah. Something like that. So we're left with cosine plus cosine over sine.
Okay, now at this point, I'm sad to say, it looks like some things could cancel. They actually can't right now. Because if I want them to cancel, I have to have them in everything. So if I had sine, sine, and sine all in the bottom, I could cancel. If I had sine on top, and sine on top, they could cancel. If I had cosine on top, cosine on top, cosine on top, they could all cancel. But it has to be in everything. It's not in everything. There's no one thing in everything. Some suggestions. As a hint, we're probably going to have to do an algebra rule. There's no way to fix it the way it is right now.
You can break it up.
Let's break it up. How do I break apart a fraction with an addition sign on the top?
Just
Sine over cosine.
2 different fractions added together.
So I have sine over cosine all over 1 over sine plus cosine over sine all over 1 over sine. This is an algebraic rule we talked about last week where I split the fraction. I can do this if it's happening to the denominator at the top. Sorry, the numerator. Oh, backwards. Sorry. So these are now 2 separate fractions. That's actually really good because one of the pieces got better. Look at that right-hand piece now. That right-hand piece has something in both the top and the bottom.
Sine.
That's sine. So the right-hand piece can now actually simplify some.
Cosine over 1.
Cosine over 1, which is just
Cosine.
cosine. Which you notice, my goal was to get everything in terms of cosine, so that part's actually golden. It's great. But on the left-hand side, it's not looking so good.
Wait, wouldn't the left one cancel out?
No, because the sine's on top of this one, it's in the bottom of that one, I can't cancel.
Oh, you can get sine squared.
Ah, so what are you doing there?
You're flipping and you're dividing.
So now, he's going to use that reciprocal rule we talked about. Oh no. Please don't. Please don't. Quick. No.
Come on, man.
I gotta talk to Graham again. Okay. I had on the previous line sine over cosine all over 1 over sine plus cosine over sine all over 1 over sine. We use an algebra step to do that. And then we said we were going to cancel the signs on the right-hand side. We cancel the sign, cancel sign. So on the right-hand side we get just cosine. Okay, now Garrett has proposed simplifying the left-hand side in a very specific way. Garrett, how are we going to do that?
Oh, you're just using your, KFC rule or whatever.
Yeah. So some of you guys, when you're in algebra, might have learned the KFC rule. So we keep the top, flip from division to multiplication, and then change from sine to cosine.
And sine squared equals 1 minus cosine squared.
So first, let's start right there. So that algebra property we had. And then he says, okay, sine times sine, that's sine squared. That's obvious.
Wait. What? Oh, you used okay, I see.
Sorry, I'm showing all the work. Now this looks really good, but notice that this has 2 things with cosine and 1 thing that is definitely not a cosine. So Garrett, you have one last suggestion. What was that suggestion?
Sine squared equals 1
Then hold
minus
it.
cosine squared.
1 minus cosine squared over cosine plus cosine of x.
What did you come to?
So you'll notice this function has everything in terms of sine and cosine. And we reduce it all the way down to just being in terms of cosine as required by the problem. Now, as it turns out, for some reason, this is not the book's answer. It looks really good. Like, everything looks great about this. We've gotten rid of every other trig function. There's no sines, there's no tangents, there's no cotangents, nothing else. It's just cosine. Yet this was not the answer they gave.
Was the answer they gave like
Of course you would.
what 1 minus like 2 cosine or something?
So, this left-hand piece does simplify farther.
Because you can split the fraction.
Let's split it again. Left-hand piece. Walk me through it there, Scott.
Oh, I wouldn't have a clue out of here.
So we have 1 over cosine
1 over cosine
minus
minus cosine squared over cosine
and don't forget the cosine in the end.
plus cosine.
Next.
Yeah.
Sorry, it's getting kind of hard to see over there. I apologize. So right now we have 1 over cosine minus cosine squared over cosine plus just cosine. All right. Suggestions. Something simplifies here.
The cosine squared over cosine
What does that become? I'm going to erase the top.
becomes
Cosine.
cosine.
And then the cosine, and then one of the cosines cancel out. And there you
That's right. So going down here, we have 1 over cosine minus cosine squared over cosine. He says one of the cosine is going to cancel.
So it'd just be cosine.
So we end up with 1 over cosine minus cosine plus cosine. So we canceled one of the cosines on top and bottom, but the negative stays with it. It stays there the whole time. Wait a minute. This looks good. What happens now?
The negative cosine and positive cosine cancel and you're stuck with 1 over cosine.
Now you might be tempted to be like, but 1 over cosine, that's secants. No. The problem specifically says to leave everything in cosine. So this is the correct answer. Now this answer down here is a good answer. We've gotten it in terms of cosine, but it's not a simplified answer, and the problems always ask for both. So if you find that the back of the book is not matching your solutions, maybe it needs to be simplified further. Does that mean your answer is wrong? It means it needs to be simplified further.
So on the test, if we like left it at that one because we didn't see
You
the
lose some
left
points. You lose some points. I know. Questions? All right.
Oh.
Do you want to do some more practice on this?
Like
Again.
them and dyeing them and everything.
We've done trig identity problems. Gentlemen. We've done trig identity problems. Right. So you begin the end. Hey. I didn't mean to talk quieter. I meant stop up. We've done trig identity problems where we actually were told at the beginning and the end you had to fill in the middle. We've done problems we had to simplify. We've done problems we had to rewrite, which also involves simplifying. Those are the 3 big parts of your homework now.
When's the homework?
Homework we posted here before you get class. Tomorrow I got to work with some more examples, going through both problems from last week and problems from today. And that should finish us out to the section.